wonderful conference. The concept of the conference I really appreciate. Thank you once again. So, I today would be talking about granular flows through apertures, and essentially, I'll keep mathematics to a minimum, basically, almost to zero, I would say. I will not talk about equations, I'll talk about physics, so which I like, and I would like to shed more light on. Some of the key questions which I think are pertinent to explore for granular flow through apertures. So before we proceed, so let me give an overview of granular materials. This we all handle in our everyday life, right? So it's a if you go for the definition, so it's an assembly of solid particles that we can see through eyes. Uh, Size typically larger than 100 microns, so no worry about cohesion. Most familiar and ubiquitous, as we said, that if you look at the materials that we use in it will go that we use in I was sharing that this we all know. I mean, the grains that we use in kitchen, pharmaceutical pills, asteroids located between two major planets, uh, sand dunes, and somewhere some other geological applications as well. And this has an integral existence. So appearance in daily routine, I'm sure all of us must have experienced. Whenever we open up a packet of chips, invariably we find larger particles on top. The question is why. In literature, we call it Brazil nut effect. So it's very interesting, and still people are trying to understand this mechanism behind Brazil nut effect. Landslides, again, larger particles, they come forward, right? So when we talk about landslides, two major questions come up. One is essentially how does basically one is related to triggering, another is how far it will go. So, but again, one interesting observation is that larger particles move forward. Industrial application, one application is shown here in rotating cylinders used in chemical engineering industries, and where if a binary mixture is rotated in a cylindrical drum, so they essentially form bands along the axis. So typical characteristics for granular materials, one is that they differ from conventional materials, which we know, right? And it can behave like, so it is underlined like a solid, a liquid, or a gas, and it depends upon the external energy input. So one example is shown here, essentially for when sand flows through an orifice in an hourglass. So typically three regimes can be distinguished here. Uh, through this cursor, let me point it out. So this static regime, which is basically the when particles after hitting the base come into rest, they form a heap. That's a solid like. This stream of grains of sand essentially it flows like a liquid, and particles which are essentially bouncing off something we can essentially imagine like gas like scenario, or some for gas like scenario another example could be sand flowing in a desert. But the key point here is that two or more regimes can coexist. So most granular flows essentially fall into in practical situation in the dense regime. What is dense regime? So here particle interactions are by collision and enduring contact. So when they are flowing, so they are flowing also and they are in continuous contact. So these are some of the examples like landslides, and when the granular discharge in a silo hopper like this arrangement, and when particle are conveyed on a belt. Some example. So the focus of the talk today is granular flow through an aperture. So again, this one small example is shown here. Sand flowing through an hourglass, and the schematic is also shown just for the sake of clarity. This is the classical problem of granular mechanics. I think I would say that 2 centuries, maybe one and a half, maybe more than one and a half, and no general consensus on several issues. And one issue I'm going to essentially touch upon in this talk today. Extensive industrial applications, that goes without saying, and it has interdisciplinary connection like pedestrian and traffic flow. So two images are shown here. So this image where the cursor is here. So this one is taken from Kumbh Mela in Ujjain last time in 2016 or perhaps. So there, see, pedestrians walk through some confinement, right? So and they have small packages essentially to egress or ingress both. So if we draw a parallel or analogy between or similarity between two systems, granular flow through an aperture like this, or so this is one pedestrian, and another one is essentially traffic flow. Again, they move this the discrete entities which are vehicular traffic. They move through confinements. Coming back to granular flow, so concerns, so basically two concerns of the scientific community. One is essentially, so let me highlight the bottom one first, this one. So we would like to develop a general and robust mass flow rate expression that for industrial application and for other applied viewpoints, we would like to develop those which can account for a variety of scenarios. Another is essentially to understand the physics behind that. So um, so the region, if we look at this schematic it presented here, so the region here close to the outlet is crucial for the outflow, and there are many unresolved issues. And I believe that this region essentially contains many mysterious things, and one is perhaps I would like to talk about today. So I would like to present some historical overview, primarily on key research attempts that have been undertaken in the past 1.5 centuries to understand the physical basis for the development of a mass flow rate expression. As I said earlier, there are two concerns. One is the development of a mass flow rate expression and understanding the physical basis also. All right, so my focus for this talk is understanding the physical basis. So one understanding that was common that emerged from, as I said, century-long efforts is that there exists a transition region right above the exit and which correlates with the flow fields at the outlet. So like here, so if something is, so this is the outlet and this is some transition region here. So what is happening here is essentially related to happening upstream. So that is one common understanding that emerged. So let us have historical excursion. So in 1852, Hagen, so pressure, we all know Hagen in fluid mechanics, right? So he conducted experiments on flow of sand through apertures, and he said something about that one expert excerpt from his paper is reproduced here, and it says that the free fall of the sand starts on the surface of the paraboloid. The keyword is free fall of the sand, right? So he said that there is a boundary right above the outlet at which the sand particles starts falling freely. In 1961, Brown shed some light on minimum energy theorem for flow of grains, and they also talked about here. In their 1965 paper, they said the kinetic and potential energy of the material in a stream tube has a minimum, and that is equivalent to the proposition that there is a free fall arch. All right, so the keywords here: free fall of the sand, free fall arch. So if I combine it, all three, so they said there's a transition region, and the transition region is called as free fall arch, where the grains fall freely under gravity, and this schematic presents it. So what does it say? It says that right above the outlet, there is a virtual boundary at which particles are in contact, and just below they are not in contact, right? So what does it indicate physically? It indicates physically that if there is a free fall arch, there has to be stress discontinuity, right? There's a free fall arch, there has to be stress discontinuity. So if I consolidate it, then Hagen what said free fall zone, then Brown and his colleague later on said free fall arch, which corresponds to minimum energy, that location. And of course, if free fall arch has to exist, then there has to be a stress discontinuity. Let us proceed. Comes the year 1961, and this relationship given by Beverly and colleagues by performing experiments that the mass flow rate essentially can be estimated by using these parameters, where capital D is the orifice size and small d is the particle size. And this expression we can essentially get through dimensional analysis also. But the important part here is that this gets the support of the free fall arch. So we also consider free fall arch. 2012. So that paper was published in Physical Review Letters. This is, in my understanding, is very important result because they used cell-similar velocity and density profiles at the outlet here to find, and using continuity to find out the mass flow rate expression. And but again, yeah, they utilize the concept of free fall arch. And this is a Spanish group, 2012. So until 12, they said free fall arch exists. Fine. 2012, again one paper came, one study came, and they said that there is some transition boundary, which is a network of contact forces but resembles like a free fall arch. Now comes the year 2015. So this Spanish group, they said this, there's no discontinuity in this stress field. So there's no discontinuity. So there's no stress discontinuity. That means there's no free fall arch. Right? So if I look at the first 2 points, that, and they also observed that near the outlet, there's no region where essentially particles acceleration equals gravity except its proximities, right? So there are gradual increases in acceleration below the transition zone. If I combine these two, so these two observations do not align with the idea of free fall arch, right? So let us combine it here after 50 years. So they revisited these people revisited the traditional notion of free fall arch in the absence of stress discontinuity, and they coined the again transition, well-defined transition in terms of peak kinetic pressure. Kinetic pressure is essentially velocity fluctuations. Now my take here is, if I summarize here, so first is there's no consensus on the physical characteristics of the boundary describing the flow transition adjacent to the exit. One, but there's a general agreement, or maybe say belief, that there exists a transition region and its connection with the outlet, like the schematic presented here. Now this is the key question which I asked. I'm going to answer this question, that how to establish connection between the transition boundary and the outlet velocity here. All right, here. What is happening here and what is happening here. And that will help us essentially to develop mass flow rate expression eventually. So that's the question. So interconnectedness of the transition boundary and the outlet velocity. Again, looking back at this paper, so they talked about self-similar velocity profiles at the outlet. So velocity profiles exhibit self-similarity. That means whatever is happening at the transition boundary, it has to be self-similar. So looking at that, I propose this hypothesis that if I need to connect the outlet velocity and the characteristics of these transition boundaries, so there has to be a dual similarity criteria. One is self-similar, another is geometric similarity. So profiles which describe the transition boundary, it should be self-similar and should be of similar shape as the exit velocity profiles. That's the hypothesis. So two things I will consider. One is essentially power, rate of energy dissipation, and another is kinetic pressure. That is given by trace of stress tensor, and these are essentially velocity fluctuations. So another is rate of energy dissipation. I'll focus on the former first. I mean on this first, rate of energy dissipation. We use computations, and this is the setup. So two-dimensional setup we consider centric outlet, basically a symmetric arrangement, and the technique that we use is discrete element method. Other parameters that we will, and we use outlet size varying between 6 particle diameter to 20 particle diameter. So 15 diameter size we have considered. So I will skip this. So computational technique that we consider discrete element method, where we resolve each particle contact and find its forces, and after finding out the acceleration, we update their velocity and positions. So let me skip this, and let me come to results. So here, so looking at the dissipation rate, so I will pick this point here at the center and go vertically and plot energy dissipation rate for 3 different outlet sizes here, and we see that it varies non-monotonically. So energy dissipation rate y equal to 0 means outlet, and when you go up, so we are going through the central line here. So for all cases, it increases and then it starts to decrease. So this location of, so this location, we call it that, I mean, where the energy dissipation peaks will collate all these along the outlet and along the central zone, which encompasses this outlet here, and let us plot that here. So y corresponds to the location where energy dissipation takes a maximum value, and we plot it between the outlet. So -1 to 1. -1 corresponds to the left edge of the outlet, and 1 corresponds to the right edge of the outlet, but that's the central region that it encapsulates. And we do it for the smallest and the largest aperture, and we see that for all fill heights, essentially, whatever be the fill height of grains, so energy dissipates largely at the same location, irrespective of the fill height. So for that, we essentially present results for height equal to 100 particle diameters. So transition boundary, here we plotted for again 15 outlet sizes, and for 15 outlet sizes. So as the outlet size grows, the transition and arch, of course, enlarges. This is expected. But when we scale it with respect to its maximum value or the value at the center, it essentially collapses. Whole data, right? So this says that the cell similarity holds. All right. So again, going back to the exit velocity profiles, which are shown here for 15 outlet sizes, and when we scale it up with its value at the center, they all collapse. This was shown by the Spanish group in 2012 in their study. So let us recall our hypothesis. What was the hypothesis? So I hypothesized that if I need to connect the outlet velocity and the transition boundary, has to be self-similarity and they have to be geometric similar, right? So self-similarity we have seen. So both are essentially self-similar, looking at the transition boundary and looking at the velocity here. So one is fixed, that they are both self-similar. Another is looking at their profile shape. So this is for the transition boundary shape, and this is the exit velocity. So if I fit this using the expression given on the top, and their exponents are given here, 0.5, they are nearly 0.5, right? So it says that both criteria are satisfied. There exists a self-similarity and there is a geometric similarity also. So then based on that, we would suggest that peak dissipation rate can be a signature of marker of transition. So for the sake of completeness also, because earlier study explored kinetic pressure as a marker of transition, and in light of the hypothesis, the dual similarity criteria, let us look at whether kinetic pressure is a candidate for a marker of transition. So we repeat the same thing again, showing the vertical profiles of kinetic pressure here, and they also exhibit non-monotonicity and peaking close to the outlet. And here for smallest outlet size and the largest outlet size, so they are independent of the height also. So that means this is important to remark here, that this says that whatever is happening, so it is essentially in the vicinity of the outlet. So outlet essentially governs the phenomena there primarily. So filling height is not of a concern here. Again, here, so when we plot profiles corresponding to peak kinetic pressure along the central zone, they are symmetric. This is expected. But again, the data when we scale it, so yk here we scale it, these values with their values at the center, whole data do not collapse on the single curve like the peak dissipation rate. This is prominent when the outlet sizes are essentially small. So Again, the criteria one for the dual similarity criteria, the self similarity does not hold for all apertures. If I remove the small ones, certainly it does, right? And when we when we fit this expression using this equation here, so we get this exponent will be nearly 1.5. But to compare it with the outlet velocity, if we can simplify this expression here, so we see that exponents are here 1.5, but for outlet velocity, this is 0.5, right? So for the case of peak kinetic pressure, dual criteria are essentially not satisfied. So we can conclude, considering the dual similarity criteria, that the peak kinetic pressure is not a marker of transition. Let me have a universality check. We can, that why can't we have connection only based on velocity? So if I look at the velocity at the outlet, velocity profiles computed corresponding to the location, at the locations corresponding to the peak dissipation rate, and at the location corresponding to the peak kinetic pressure, all, I mean, they are self similar in all cases, and their profiles are also similar essentially, that the profile shapes. So what does it say? It says if I look at collectively the features which these profiles exhibit, so they appear to be universal. You know that the location at which the dissipation rate peaks and the kinetic pressure peaks, they are two different locations, and this is outlet, and of course, so this is one location, this is another location, this is another P, and kinetic pressure is another location. So it says that these profiles are appear to be universal, that is independent of the location and shape of the region at which velocities are computed, because we have seen the shape of the region for kinetic pressure, peak kinetic pressure is essentially different. So consequently, considering the similarity between the velocity profile seems to be a redundant thing. We will not consider it. So this again justifies utilizing similarity only between a transition boundary and the exit velocity profiles for characterizing the flow transition. So this point, I would like to justify that why we are not considering only the velocity and why the shape is also important. So that's the summary. So in light of the dual criteria of self-similarity and geometric similarity, we demonstrated that the peak dissipation rate is a plausible signature of or marker of transition in granular flows through an aperture, and the emergence of the peak kinetic pressure does not appear to a marker of flow transition. And if I combine it here, so essentially we stand here. So they said free-fall arch does not exist. Peak kinetic pressure is a marker of transition, and my study said, based on the dual similarity criteria, peak kinetic pressure does not appear to be a marker of transition. Peak dissipation rate essentially a signature of transition because its shape and its shape also relates to the velocity outlet profile. So if you would like to read here, so this was published last year in Physics of Fluids as a letter. Thank you for your attention.
So anyone having any questions regarding questions?
Number of particles.
Yeah, does it affect your theory?
Number of particles are essentially, you look at the filling height, because I'm keeping this width same. So now if you increase the number of particles, the filling height will increase. So that we have said. So
No,
filling
if
height,
you're a smaller particle, bigger particle, and are those in same height,
that
does it affect any your hypothesis or have
No.
any influence on your hypothesis?
if we change the mean particle size, it doesn't affect the hypothesis. Self similarity holds in that case.
Okay.
But the shape also, that I need to investigate. But self similarity of the peak boundary, that the boundary corresponding to the peak dissipation rate, that it holds.
Yeah, looking your work, I remember my childhood days in my village where we have silos, big silos, and grains are stored in over the year, and then we open it. Something this is coming up, but I believe different grain have different kind of arc and all those things.
Correct.
So not sure that grains of different size and shape may affect your velocity. Certainly, I remember I tried to connect it.
Size study I have done,
Okay.
considering because this is a polydispersed mixture which I have considered.
Okay.
Having a polydispersed 20% polydispersity. So, so by reducing the mean size, that I checked that the non-monotonicity of the peak dissipation rate, it holds. It is self-similar, it holds. But their shape with the outlet velocity profiles, perhaps I need to check how would it distinguish. But and I varied the frictional parameters also.
Between
Very-
the particles.
huh?
Between the particles.
Yeah, between the particles, very smooth to very rough. It still holds, and interestingly, the exponent does not vary much in that case.
Okay.
So this is first part of the study. Second part is essentially to develop the flow rate expression, because now I have demonstrated that peak dissipation rate characterizes the transition boundary. Then this shape and the outlet velocity profile, I'll try to connect and then come up with the flow rate expression. That's it.
Thank you.
Sir, can you tell what is the application of this study?
Application, I said it earlier. This I looked at from the fundamental viewpoint. I said, so there are two things. One is we would like to develop the flow rate expression. If I have the expression in hand, so I don't need to conduct experiments or simulation. I can simply work out the flow rate, right? Another part is that how does the, so basically the physics behind that. So I focused on the physics here. Another next step is essentially to find out the flow rate expression, right? But this thing, so the parallels, the similarities, if you see granular flow through apertures, is, let's say, let me take this example. Suppose because of some emergency, if you need to move out if you need to move out from this room, right? From where we'll move? Through this door, right? And this door is essentially a narrow exit. All right. So, so having these studies essentially try to shed light, essentially to design such systems as well. Okay. So another is traffic flow as well. But from this study, I would say I mean I was quite surprised and pleasantly surprised to know that near the aperture, this is essentially energy sink. Perhaps I'm saying it very loosely now because I had to consider the time scale there also. But it's an energy sink, that dissipation rate is getting very high there. So many applications it comes. At the outlet, velocities are very high.
So how it is in, near to outlet? You said it is a energy sink. Yeah, energy sink. It means
Energy dissipation rate is high.
so it losing the kinetic energy and basically velocities would come down.
No, velocities are
I'm
increasing.
contradicting something.
Huh?
I'm contradicting something.
No, velocities are high near the outlet. That's what I said. Because if you look at energy dissipation rate,
Okay.
to make that comment appropriately.
Probably something going against my intuition, but yeah, we'll discuss later offline. Yeah, yeah. Because now, I clearly remember my childhood days. I said in village, people used to store the grain in the silos, big silos, and they're opening it, and grain is coming out. So I now is able to imagine how grains were coming in, and grain for wheat, rice, and corn are totally different,
Correct.
and peas and all those things are very different. So yeah, it's a very nice talk. Okay, thank you.
you.
So we extend our heartfelt thanks to our professor Ashish Bhateja sir, and
we now would like to request Dr. Anup Kumar sir and Dr. VP Sharma sir to, and sorry, Rajesh Prabhu sir, to felicitate our keynote speaker, Dr. Ashish Bhateja sir.
Moving on to our next keynote session, I'd like to request Dr. Anup Shukla sir, Dr. BP Sharma sir, to present Tulsi sapling to Professor Dr. Aman Rath as a token of gratitude. Please join us on stage.
The topic of Professor Dr. Amonrod is flame characteristic of NG combustion on innovative spiral Bluffy body axial burner. Associate Professor Dr. Amonrod is a lecturer in the Department of Mechanical Engineering at the Faculty of Engineering, King Mongkut's University of Technology, Thornbury. Her academic and research pursuits focus on both external and internal combustion. She serves as the Vice President of the Thai Society of Mechanical Engineers, comprising members from various mechanical engineering departments across Thailand. Her primary research involves analyzing gaseous combustion flames for clean combustion, developing smart burners, and innovating novel energy generation methods. Her work includes investigating the combustion flames of municipal solid waste, biogas, and hydrogen through cellular flame analysis, enhancing slot and axial burners for flow emissions and high efficiency, and designing microcombustors to achieve high energy conversion efficiency. Now, I request you to carry on with your address.
Thank you for introduction, and also thank you the organizing committee for inviting me to join with this conference today. First of all, I would like to present the title of my research that concern about the flame characteristic of natural gas combustion on innovative spiral body axial burner. So first of all, I would like to a little bit introduce my university. So maybe I'm not sure. Maybe some people maybe know about my university first. And my university, King Mongkut University of Technology, Thonburi, is located in Bangkok, Thailand. So how far from Amity University? Around 4,000 kilometers from here, and around 4.5 hours by flight. And if you are interested about KMUTT and also would like to join with us, so please contact with our website and also the Facebook. So this is just the brief of my university. So back to my research today. So my titles that concern about the burner. So first of all, I would like to show about the motivation of our research. So regarding the statistic of the investment of energy, so you see the trend or statistic of fossil fuel. For example, coal oil and natural gas. You see the natural gas is one of the fossil fuel that apply and also invest as the energy, as the important energy in the world. And this is important for our study. And moreover, the natural gas, what is the important for natural gas? Because in Thailand, especially, I'm not sure in another country as well, for apply the natural gas combustion for power plant. So in Thailand, maybe more than 60 or 70% of power plant apply the natural gas combustion. So that's why we are interesting to study about the natural gas combustion in power plant. And also, if we need to understand about the natural gas combustion, so especially for the power plant. So in case of natural gas combustion in power plant, the axial burner is the one of the important burner that apply in the power plant. So you see like the axial burner in the gas turbine and also the engine in, and also the burner in the power plant and also in industrial burner as well. So back to the natural gas composition. So normally, I think you can find out the composition of natural gas in the world. There are many compositions of natural gas, such as the methane, ethane, carbon dioxide, and any other composition. And in Thailand, for the main composition that we concern about the organizing for the power plant. So we concern about the average composition around methane, 89% of methane, and also 11% of carbon dioxide. And any other components such as the ethane, nitrogen is important, but a little bit composition compared with the main composition like methane and carbon dioxide. So in this study, we focus on only the methane and carbon dioxide as the composition. So any other important thing for this study, and this is very important for the burner. So maybe you know about the burner, right? But I would like to show you about the difference between NDF normal diffusion flame axial burner and IDF inverse diffusion flame burner. The axial burner different. So originate axial burner is NDF. So maybe you know exactly because the fuel is inside and the outside is air slot. And in order to develop the axial burner, so the IDF is developed to change the air slot is inside and outside of fuel. So when the IDF axial burner changed the design, so what happened? So the fuel is mixed with the air inside and also the environmental inside, external air, and also the list of flashback flame and high efficiency and also the high temperature will be obtained from the good mixing between air and fuel. So that's why IDF burner or IDF axial burner is very important to study more. And from the previous study in our laboratory in 2020, so this is the result from the experimental experiment. And from this result, you can see the at boiling rate around 2 kilowatts. And we will obtain on the axial burner that this is the design of nozzle axial burner. So we will obtain the stable flame and also the blow off limit. We will observe around less than 0.12. It's very low comparison between any other burner. And the flame temperature we also obtain at equivalence ratio 1 around more than 1300 degrees Celsius. So the comparison between this flame temperature is high or low. Comparison between the adiabatic flame temperature of natural gas is around 1900 degrees Celsius, around approximately. So comparison between adiabatic flame temperature, so we have possibility to increase the flame temperature as well. So in order to improve the flame temperature or combustion characteristic of natural gas combustion on the burner, so it's necessary to design many characteristics of burner. So this is we need to focus on the burner firstly, and the diameter of the air slot and fuel slot is very small, only from the reference design, only 7.5 millimeters and around 14 millimeters, so very small. So in order to improve the flame temperature or the combustion characteristics, so it's necessary to maybe enlarge the burner firstly. And in order to increase or enlarge the burner, so we obtain the first or the reference burner result. So comparison between the reference result, we need to enlarge the size of burner with the same result, with the same temperature, the flame temperature. So we would like to study with the reference burner and also use the enlargement for the burner, the reference burner. And then when we enlarge the burner and also we also achieve the same condition, the same result of the enlarged burner, and then we improve the burner by the by the design of the new burner. So in this study, we will apply the spiral buff body technique for the enlarged IDF axle burner. So this is the chemical reaction for the natural gas combustion. So in as I ever said to you, for the composition of natural gas, so that consists of the 89% of methane and 11% of carbon dioxide. So this is the chemical reaction for that. And any other equation that we also apply by equivalence ratio fuel rich stoichiometric mixture and also the lean mixture. In this study, we also focus on the stoichiometric mixture and also the lean mixture to observe the blow off limit of the flame of the fuel flame. And any other important thing for the enlargement, so we also concerned about the dimensional analysis of similarity. The similarity, so you can see in this figure, normally the similarity rules. So we need to obtain the enlarged size or the down size of the main thing that we need to study. So in this study, we need to enlarge, right? So the same result and the similarity is necessary to apply for this study. So in order to apply the similarity rules, it's necessary to know about the important parameter first, because in case of flame burner, so we need to concern about the firing rate, flow rate, lower heating value, density, and burner length. So it's necessary to concern the burner length and also the burner diameter as well. So we need to concern about this impact parameter for this study. And then, so we apply the enlargement study for the by the ANSYS Fluent program, and then we also applied the ANSYS program with the any setup for the model calculation. And also that you ever seen about the important parameter in the previous slide. So of this slide, we also apply the similarity rules with the important parameter, and then we will find the diameter and also the length of the burner that we need to enlarge. For example, enlarge to double, triple size something. So we also try to apply. And from the similarity, we also apply from the left side hand. This is the dimension of the model of 2 kilowatts diameter. So from 2 kilowatt of firing rate dimension of the burner. So from this dimension, we try to enlarge for 4 until 20 kilowatts of burner. And from in order to enlarge the burner, so we need to apply this similarity result to obtain the dimension. For example, the length and the diameter of the burner as this table. From this table, we will obtain the result of the flame temperature from 2 kilowatts and until the 20 kilowatts. From this result, you can see the flame will be enlarged and also the higher flame, right? So it's because of the higher firing rate. And you can see the same characteristic for the combustion, for the natural combustion on the enlarged size of the burner. And comparison between the flame temperature 2 kilowatts until 22 kilowatts. So you can see the difference between the flame temperature is a little bit changed around maybe 3% of error. And not only the temperature, but also the average velocity. So we also obtain maybe less than 2% difference of the average velocity between 2 kilowatts and 2 kilowatts to 20 kilowatts of burner. And comparison between the linearly analysis or linearity. So linearity, what does it mean? It means if you need to enlarge the size of burner 2 times, 3 times, so you can use the filing rate and use the only the filing rate is the size of or maybe predict the size of the diameter and length. This is the directly predict for the burner. So you will see about the filing rate 2 until around 10. So we try to predict about the linearly analysis. And from this linearly analysis, you see, okay, the flame will be enlarged and higher, right? Compare between the 2 kilowatts of burner, and you see moreover the difference between the flame characteristic. You see like the cool spot comparison between this 2 kilowatts, but you can see like a cool spot around maybe the light green, light orange of the color scale around here. And this is a little bit different comparison between the uh, linearity and also the similarity. So another comparison between the similarity and also the linearity analysis. This is a flame temperature. So you see the orange part. The orange is the linear analysis. So you see the similarity analysis almost close to the 2 kilowatts burner, right? And comparison between the orange part. So you see big difference between the linear analysis and also the reference burner. Moreover, average velocity as well. So you see less than maybe less than 2 or 3% of average velocity difference comparison between similarity with the reference and linearly or linearity analysis. You see the big difference or quite different with the 2 kilowatts of burner. So not only the simulation result, but also we need to know about the experimental result as well. So this is the experimental setup for our study. So you see, this is the methane, carbon dioxide, and also air compressor, and this is the actual burner, and this is the design from the simulation. And finally, we obtain the result of the flame and also comparison between the simulation result as well. So you see the characteristic of the actual flame, the photo flame. So it's almost same, right? And a little bit a little bit higher comparison between 2 kilowatts to until 2.53 to 0.54. And actually, in case of simulation, so we also we can study the simulation from 2 kilowatts to 20 kilowatts. But in actually, so 20 kilowatts is too high, too big for our laboratory. So that's why we try to study only 4 kilowatts. And in case of 4 kilowatts, you see the difference of flame temperature between 2 kilowatts and 4 kilowatts. So you see a little bit change from the reference model. And as same as with the result of simulation, so you see almost same simulation by the similarity result. And this is the result of flame temperature. This is a relation between the filing rate and the flame temperature. You see almost same of the result. The blue result is the simulation, and the experimental result is orange color. So comparison between simulation and experimental result. So you see maybe less than 5% different, and it should be almost same between 2 kilowatt and 2.5, 3.5, and 4 kilowatts of burner for the frame temperature. So we obtain like that at the equivalence ratio 1. So this is the result of experiment at 2.5 kilowatt, 3 kilowatts, 3.5 kilowatt, and 4 kilowatt. So you will see almost same flame characteristic, and also the flame temperature. Flame temperature a bit different, but not same, but a bit different. But this flame temperature we also acceptable for this different, a little bit different. And this is the comparison between the flame temperature, and you see equivalence ratio. When equivalence ratio decrease, exactly the flame temperature decrease, and almost flame temperature at equivalence at a filing rate 2.5, 3, 3.5, and 4 almost same, and frame height almost same. So in order to compare between the enlargement, that we need to apply the enlarged burner for the next step for our study. So we will see the almost same, almost stable flame, and also following the flame temperature and flame height, we also obtain the reasonable result of the enlargement that we also obtain from the 2.5, 3, 3.5, and 4 kilowatts. So that's why I think the maximum that we also obtain from the result, that is the 4 kilowatt. It is the stable flame we also obtain. So that's why next step we will use the burner of 4 kilowatt of filing rate to apply for the next step of our research. So this is like a little bit video. So next step for our study, so that I will say to you for the spiral black body axial burner. So maybe you know well about the axial burner, right? And the spiral black body is the black body that we also apply on the axial burner. This is the technique, our technique that we try to apply to adjust to study about the flow rate of the air. The spiral black body will be put it on the middle of the air slot. So from this figure, you will see about the position of the spiral, the black body, the spiral black body on the axial burner, and how different between the S1, SH, S10, and S12, 1, 2, 3 models. The difference is SH means 8 millimeter with the M8 trace for the bulb body. So this is the size. This is the small size, smallest size, the medium size, and the bigger size, the biggest size of bulb body. So how different? Because when we apply the small size, so you see the flow rate of the air will be flow, and we need to know about the size, the proper size of the bulb body, and also the trace. What is the proper for the axial burner? So this is the result of the simulation. First of all, we need to know about the flame temperature and also the flame characteristic. Firstly, the temperature distribution or the flame characteristic between H, S10, and S12. So the three of model, we will see like the flame length of the S12 or the last one is a little bit shorter comparison between S10 and S8. And any other result, you can find out the flame temperature of spiral S12 is a highest comparison between the S8 and S10. So from this simulation result, so you will see the last one is we obtain the highest temperature, right? But you will see it's not obvious compare between the flame temperature of S8 and S10. So that's why all of this design. So we will, I think, is the comparison between the smooth or original burner. So we need to develop for S8, 10, and 12 as well for the experiment. So that's why I will obtain the experiment for all of three design. So in case of smooth, so this is the result of reference that we also enlarge the burner, and we will get the temperature almost same with the reference at filing date around 4 kilowatt. And in case of development S8, 10, and 12, we also obtain like a blow off or quenching flame at the S12. So we cannot ignite the flame from the S12. And in case of S8 and 10, so the size of bulb body increase when the S increase, right? And this is the kilowatt that we can obtain the ignition of flame at only 3.2 and 2.2. So we can obtain the ignition flame around this kilowatt, maybe less than the reference filing rate. So comparison between only the ignition flame, ignited flame, so for S8 and S10. So we neglect for the S12. So you see the flame quenching will be observed on S12, and also the stable flame will be obtained the widest around maybe less than 0.7, and is only less than 0.8. So the widest flammability limit, maybe I'm not sure everyone maybe know about the flammability or the important for the flammability limit. So if you need to apply the burner, so the flammability limit is important, because if the flammability limit is very narrow, you can ignite, you can get the flame. It's very short time, and it's least for the flame quenching or blow off flame, and is maybe bring about to the accident for the application as well. And comparison between the flame temperature with the equivalence ratio, you see the S8 burner, so the blow off around less than 0.8 that, and the maximum flame temperature we also obtain around maybe more than 1356, and S10 we also obtain the blow off at maybe less than 0.7, and flame temperature 1273. And S12 burner, we didn't obtain the flame and the flame quenching first. And comparison between the smooth burner at 4 kilowatt, the blow off or the flammability limit. Okay, so at the equivalence ratio 0.2, and the maximum flame temperature around only 1300 degrees Celsius. So comparison between the S8 will obtain the increasing of flame temperature, and maybe the blow off flame or the flammability limit is narrower. This is the disadvantage that we obtain from this experiment. So this is the conclusion for our study. So that I have said to you for the smooth, the comparison between the reference burner, the smooth burner at 4 kilowatts, and S8 at the 3.2 kilowatts. So that I will obtain the first ignition flame. So comparison between it is the design. So you see this is the black body on the middle of air slot, right? And we obtain also stable flame, and the flame temperature will be improved around 3.5%. And from this study, not only the temperature increase, but also we also obtain the disadvantage and also the thing that we need to improve in the further, such as the flammability limit and also the quenching flame. So this is all of my study. Thank you very much. This is our supporter in Thailand. Thank you. Do you have any question?
Very impressive work. I really appreciate. Okay, so my background is computational, and mostly I'm working in thermal radiation side, where radiation is emitting from the CO2 and S2 gas, and most prominent application is this, whatever you are doing. So my question would be around this thing only. Okay, so first of all, I would like to know, you have also performed the computational work. Did you consider the thermal radiation model in your computational work? Yeah, thermal radiation model.
I didn't concern about that.
Yes, sir. Yes, ma'am.
Didn't concern about that. We just concerned about the flame temperature.
Yeah, flame temperature, but role of radiation is to remove the energy. So it the in computational work, if you include the thermal radiation model, the flame temperature will further come down.
So
Okay, so did you use until unless you are including all models, the computation result would not be equivalent to experimental result. You are comparing your computation result with experimental results. So I believe thermal radiation would be also a important component in your modeling.
So
So
think about the thermal efficiency as well, but in this simulation and also the experimental comparison. So I think the flame temperature is almost important first, and next step I think if we have maybe any other setup for the thermal efficiency, so we try to.
yeah, because literature says if you include thermal radiation model, flame temperature comes down around 150 200 kelvins, and peak temperature down by 150 200 Kelvin is sufficient. Is great importance. That's I want to know. No, you haven't used any thermal radiation model.
Okay, thank you very much.
Have you used or not?
Really, you use the ANSYS or
ANSYS, but ANSYS you have used turbulence model. Okay, thermal radiation model and
Okay.
chemistry. Which chemistry model did you use? Any chemistry model? Combustion model?
combustion model.
Which model?
Which model? Maybe pre
Flamelet model.
premix. Yes,
Premix flamelet model.
not premix.
Preliminary model is there, or
Freeze.
ET breakup model, or the ET dissipation model. There are a lot of combustion models are there. And how many chemical reactions have you used in your combustion?
Chemical reaction.
How many steps? Globally, so one step reactions or detailed chemistry have you used?
How many steps? I'm not sure. I just wonder that I didn't get the data from the step.
Okay.
The mesh that I use for the ANSYS, I use maybe less than
Yeah,
500,000 mesh for the.
mesh is different. Okay, the whole reaction happens. So if you're going for a methane combustion,
Okay.
the whole reaction happen in around 325 reactions, and there are around 80 species are formed. So different computation, the efficacy of a computation model depend upon how many reactions are you considering. And if you are basically using a global reaction,
Okay.
then what would be the equation and what is the equivalence number, all those things.
Okay, I would like to explain. So, firstly, for the ANSYS program, so this is the student version, right? First, because now we have the commercial program, but the previous study we also obtained the student program. The student version is limit only the 500,000 mesh. So that's why I just obtained the result as you can see. So from this result, I can predict for the the design of the property and the enlargement as well, but not correct, not the 100% comparison between the experiment as well. I know that, but I try to know about the trends of temperature, flame temperature, or trends of maybe flame characteristic, and also any other effects for the enlargement and also any other design. And comparison between that, you can see S12 is different from the experimental experiment and simulation experiment. Is very quite different.
Yeah, I had another question, add-on question on that. That if you're using thread, basically you are changing the wall roughness, and the wall roughness is affecting your turbulent flows. So you are enhancing mixing. So how you are basically tackling in the computational? Basically, model near to wall models are very ad hoc until unless you go very accurate model. So how did you model the thread in your computational framework? So yeah, because I'm computational, so so yeah, so very nice work. Okay, I have a lot of questions, but we can discuss
about
offline.
different between the simulation result and experimental result, but I think it would be better to do the experiment with our simulation result, because I don't know about that or the prediction between the burner design. So if we obtain the simulation result, as you can see, this is the the guideline for our experiment. Even the result is a little bit different. So I will get the higher temperature as I want. Um,
Yeah, okay, that is fine. Yeah, most of the time, computational result matches with experimental result, but most of models are missing. So it looks like physics. You're going to explain anything through computational, because computational is going to give you whole detail what is interplaying between the phenomena, different phenomena. So you're going to explain that something is missing. So thermal radiation is always neglected. I understand that thing, very complex thing. So, but yeah, anyway. So it was a good work. So
Okay.
if
Thank you for
I,
your
I will contact you if I need something or experimental thing, because we are testing our radiation model. We have developed radiation model and included in Fluent as well as through UDF. So some experimental results, if you need it, then certainly I will contact you. Thank you.
Thank you very much. Thank you for your suggestion. Okay.
We extend a heartfelt thanks to our keynote speaker, Professor Dr. Aman Raj, for delivering such an inspiring and thought provoking presentation. Your insight and expertise have greatly enriched our understanding.
I would request Dr. Suvandan Saraswat, Dr. Sumit Sharma, and Dr. Meeta Sharma to felicitate Professor Dr. Aman Raj. Now we are moving towards our third keynote talk by Professor Dr. Sandeep Patil. I request Dr. Meeta Sharma, Dr. Sumit Sharma, and our session chair, Dr. Suvandan Saraswat, to present a Tulsi sapling as a token of gratitude to him.
The topic of his keynote talk is nanofiber technology and its commercial application, future startups. Dr. Sandeep Patil is the founder director of eSpin Nanotech Private Limited. With a distinguished background in material science and nanotechnology, Dr. Patil led groundbreaking research and development initiatives specializing in the synthesis and application of nanostructures for diverse industrial applications. He holds a PhD in nanoscience and nanotechnology and has authored numerous publications in peer reviewed journals, contributing significantly to the advancement of nanomaterials. Dr. Patil entrepreneurial leadership has been instrumental in driving innovation and commercialization in the nanotech industry, establishing eSpin Nanotech as a fortuner in cutting edge nanomaterial solutions globally. Now, I would request our keynote speaker for this session, Dr. Sandeep Patil, to deliver his keynote address. Thank you.
can disconnect this. What happened? Yeah, it's done. Thank you. Good afternoon, everyone. Um, नहीं नहीं अभी करने मेल कर दीजिए किसको मेल करें? पीपीटी को किसको करें? हाँ हो गया देखिए, तो बीच में चला जा रहा है। इशू है तो आप मेल कर दीजिए ऑडियो वाले। ठीक है, अब चलेगा। Hi, good afternoon, everyone. Thank you, Amity, for this invitation, and Professor Basant Sikarwar, my friend, for invitation. I am Dr. Patil, Director ESP Nanotech Private Limited from IIT Kanpur. This is the company where I started during my PhD, and we could able to reach to the level where we have done a lot of research in nanofiber technology. So this is our innovation center located at Kanpur, where we have the facility that it is DSIR approved by the government. We are doing a lot of research related to the nanofibers, and then we have a manufacturing of large scale nanofiber membrane technology for various applications. We'll talk them one by one. So I'll be talking about today is this is related to the nanofiber technology and its application moreover in industrial domains. And what are those? Like there are many, but whatever we have developed so far in our company that is already implemented, and many of them already used in commercial domain. Everybody knows what is nanofiber technology, and what is the dimensions. So moreover, like it's very in a very straight way. It's a very simple things to like bigger things can be converted into the smaller thing. But the smaller thing can be from micro level, millimeter level to centimeter, centimeter to millimeter, millimeter to micro, and then nano. You can see this picture where the human hair is standing on top of the nanofibers. On this, can I have the pointer or something? Okay, so this is the human hair, which is basically placed on the on the base of nanofibers. You can see the half of the picture is covered by the human hair, and below that you can see billions of nanofiber are sitting. So this is the scale of dimensions. Bigger scale, you can see visibly very clearly, that is like, and then you have the nanofibers. So what makes difference when you scale down? So you can see we are like able to reach the level where 50 to 100 nanometer can be spun with using our technology, that is electrospun nanofibers. Once you reduce down the scale, of course, the surface area get increased and enhanced. Then you will get the lower density related to that, and more surface area which is exposed to the various different applications, including air filtration to water filtration, catalysis to biomedical applications. What makes difference like these nanofibers? So, but more importantly, how one can do it, and there are many synthesis routes, many synthesis processes where you can make the nanofibers in a different ways.
So drawing, thermal induced phase separation, template synthesis, fiber self-assembly, centrifugal spinning. These are the various methods where one nanofibers can spun or maybe microfibers can spun. Each and every method has their own merits and demerits. The method that we are talking about here is the electrospinning technology, where it's a very simple and one-step process. You just have to use a polymer as a solution with a solvent. You use that, apply the high voltage. There will be a potential between the electrodes, negative and positive. In this negative and positive electrodes, you just have to apply a critical level of high voltage, and that voltage can be starting from 5 kilovolt to 1000 kilovolt, sorry, 100 kilovolts. So this is a DC power where you can, okay. So this is a DC power source where you can apply the high voltage. As I said, can be from 5 kilovolt to 100 kilovolt. You can see this is the geometry of cone. When the moment you apply the high voltage towards the positive electrode, this is a syringe which filled with the solution. Solution can be a polymeric material which is linear chain, and that can be made with the solvents, and solvent will be a very highly polarized solvent where you can add a polymer with a certain concentration. With that concentration will help to spin the polymer. So see, I mean, it's very simple. Initially it was a solid, then you created a solution with a solvent. The moment you start spinning it off, the solvent will get evaporated, and at the end you will get again a solid polymeric material in the form of nanofibers. This is a very simple way to do it. And what are the things like, you just have to apply the high voltage. This is a positive electrode, this is a ground. During this, there is a very high electric potential that is basically a driving force behind to spin the material. So this is a kind of cone that can be formed during the electrospinning. From bigger thread, the smaller threads can be created. So this is the technique that we started. This is the method that we started modification of electrospinning technique. Though it is a very old technique, like 100-year-old, but nowadays it has a lot of potential in the research domain as well as in many applications. What are the forms of nanofibers that you can create? So this is a solid nanofiber, then hollow porous nanofibers, fibers with the particles, and then you can get the porous nanofibers. These are the basically forms that you can able to create using electrospinning technique. More than that, depends on what kind of polymer, what kind of fibers that you are going to use in which applications. These are the major application areas where you can use the nanofibers in the environment, electronics, energy, defense, health, automotive, building, and consumers. So considering this scenario, we have created few of the models. This is the first model that we created. Then this is the second model. This is the industrial line of nanofiber spinning, where you can make a width of 300 mm and the length is continuous. You can quote almost like 500-meter length by using this technique and this technology. That is the one that I could able to show you is a very simple way to make the nanofibers. But how you can pattern them? So to make the pattern them, we have also created the technique from the large distance electrospinning to the near field electrospinning. Near field electrospinning is something where in the first case, two electrodes are apart, like 10 centimeter to 15 centimeter is a distance between two electrodes. Here, the distance is only a few mm. So maybe you can say maybe 1 mm to 2 mm. So you can create nanofiber patterns by using the near field electrospinning. We could able to create a very nice mesh of nanofibers. Okay, of course, this is the mesh which we can easily see by naked eyes. But on these structures, there are billions of nanofibers are spun. You can see these are the structures, and where you can use this. Basically, these structures are used in biomedical field to cell growth, see the cell culture and all those stuffs. Then what we have done, we have used the same technique for the sensor manufacturing. You can see between these two wires or two metal things, you can able to see very small wire here. That is basically a suspended nanofiber. And that suspended nanofiber can be connected with the two electrode system, and this has the very large surface area. Even you can able to detect a very small minute ppm ppb concentration of the gases. Again, we have used the same technique, but modification of the same technique can able to manufacture the electrodes, sensors. Then this is again a very unique example that we could able to do with the one of the company called Mitra, and this is a strength. A strength nowadays. I mean, there are many research, many challenges are going around the biomedical field, and this is one of the another application where how one can make more suitable strength, how one can make strength as a material for the biomedical application. So this strength is coated with the nanofiber. Basically, what happens once this foreign object is inserted in your body, it acts as a foreign material for the body. So there is a body fluid formation. To avoid that, what one can do, we have given a solution where nanofiber can be coated, so it will be more compatible to the body, where cell can grow and it can have a longer life. Similarly, this is a hernia mesh. This hernia mesh is just like a polypropylene mesh, which is having a very small narrow openings. Again, this has a similar problem where it creates the as an act as an body foreign body into the human body. So again, there is a body fluid formation. So we have coated a very thin layer of nanofibers along with the nanomaterial on top of the hernia mesh, where it will act as a biocompatible implants. This is the another example where we worked with the Zim Lab, that is basically one of the pharmaceutical company, in which they wanted to create waterless medicines. Waterless medicines in the sense there we have two different formulations of the medicines. One is a solid and one is a suspension. So suspension is given to the kids or maybe the elderly people. The solid can be given to the people who can easily swallow. So what happens if you cannot fit the suspension to the kid? So what will be the solution? Solution is like, we have created a nanofiber based strips, and they will disintegrate into your mouth very easily without taking a water. So that will be immediate dissolution of the material. And how it can be? So see why, again, you may ask me the question why electrospinning is a technique can be used. Electrospinning is a technique where it works on the room temperature. So if you want to create something where you don't want to disturb the molecular orientation of the molecules or maybe the drug, you can use the electrospinning as a technique where it can be done in a room temperature. You can coat a layer of nanofibers on top of any kind of support, and that can be used for the medical application. And this is the one of the classic example of the nanofiber as in the medicine, which can use as a disintegration strip for kids, not only kids, for the elderly people also. Why elderly people? You cannot carry always water, and always, elderly people, they have a very difficulties to swallow the solid drugs. So this is again a like kind of solution. They can just chew and this will disintegrate in their mouth. This is the another example. Another technology and the product that we have developed, that is called the wet spinning technology, with highly porous structure in the hollow fibers, where you can have a multi-layer of porosity where start from the micron in between the capillary or nanometer, 20 nanometer, and then you can have again lesser than the 20 nanometer capillaries, where you can able to reach to the level where virus and the bacteria can be filtered out. So this hollow fiber technique we have used not only electrospinning but hollow fiber technique and the electrospinning coated nanofibers, where you can separate virus and the bacteria. How it can be implemented? These are the hollow fiber used membranes, like ultrafiltration membrane can be used. And the beauty of this material and this technique is like you can able to filter water at gravity pressure. You don't have to use a active pressure to filter out the water. So similar, what exactly you are able to do, like you can fit. The Tata Swatch which is there in the market, the Tata Swatch is basically coming with our filter. This is a hollow fiber filter to filter out virus and the bacteria. Like again, if you do the cost estimation and the cost calculation, this provides the 20 paisa per liter water, and this can sustain for 2 years and more than that. So you can imagine where there is a TDS level is less than 500 TDS, you can easily use this technique for your drinking water systems. Why? I mean, see, this big debate for the which water should be drink. Either we should drink the healthy water, either we should drink the clean water. Today, most of the Noida city is drinking the clean water, not the healthy water, to be very precisely. So, why we need the healthy water rather than the clean water? Because healthy is something where you have the all minerals. Clean is something you don't have anything. It's just water. So, what you need is the healthy water, not the clean water. So, this is another technique that we have developed using electrospinning, and that is related to the agriculture field. This is the project which is supported by Engineers India Limited to develop something for the farming community, where we have developed the technique of electrospinning can spray a nanofiber on the field. And what you can do with that, you can enhance the soil quality by incorporating the rhizobia bacteria into the cellulose material. You can spray this material, like let's say maybe 1 liter of solutions can be sprayed on 1 acre of land. What is there in this technology? This can be fed with a tractor. Tractor can go around on the field and it will spray a nanofiber on top of the field where you can have bacterial infused material. This nanofiber will help them to grow a bacteria fast and it will enrich into the soil. It will enhance the soil quality. Similarly, this technology can be used to spray a pesticide in a controlled way. You can also control and also targeted spraying technique where the potential can change of the molecules from positive to negative to attract towards the and like the killing the insects. Okay. This is the tractor where this is fitted and we could able to spun. This is a team they have visited to show and see how it is working. This is another technology. I mean, not another technology, electrospinning technology for the large scale. We have developed this technology not for the only the batch scale. This is a continuous line can coat a layer of 1.6 meter and length is infinite. Using this technique, we have developed the nano HEPA. HEPA is the technique which is widely used in air filtration technology today. And HEPA is basically high efficient particle arrest technique, mostly based on the glass fibers and other polypropylene fibers. So integration of nanofiber, we created the HEPA, NHEPA. N is the nano, HEPA is the technique, which is already there. So using this technology, we have developed like, decorated nanofibers with nanoparticles to not only to separate finest particle lesser than 20 nanometer or sorry lesser than 100 nanometer, but along with that we can have a decorated particle assembly which can kill and anchor the virus and the bacteria. And these are the results which we could able to showcase with our NHEPA technique, starting from the 0.3 micrometer particles to 20 nanometer particles. More than that, it also filters out the pollen and other impurities in the presence in the air. Using this technique, before COVID, we invented the mask by using nanofiber technology, and that was in 2017. And using the nanofiber, why nanofiber compared to any other filtration units? Filtration membrane that are available, which is Melblon polypropylene. See, if you use the Melblon, it is a static physical separation, but also works as a static separation. But more than that, the moment you start using the more layers, you will have the suffocation and the breathing resistance is very high. So using the nanofiber, we could able to reduce down the air resistance, breathing resistance, and you can able to even filter more efficiently the particles as well as the virus and the bacteria. This was during COVID, we have developed, this SOSA mask, and we started our manufacturing at IIT Kanpur, along with the help of IIT Kanpur and our SIDBI Incubation Center and Eastman Nanotech started manufacturing in the campus. Why it was timely needed. We could able to make only 5,000 masks per day, and there was a demand immediately between COVID, how we can increase a capacity from 5,000 to 25,000. So within the span of 2 months, with the help of our incubation and IIT Kanpur, we started manufacturing from 5,000 masks to 30,000 masks per day. So this was to serve the impact, to serve the community in a better way. This is the another technique and the method using electrospinning that we started. We invented and it is going to be commercialized very soon. It is handheld electrospinning machine used for the burn patients. So burn patients, you cannot do bandage, you cannot do anything. They have to be like, untouched. So this is the method where you have the biopolymer and the spray with this handheld gun on their bodies. So there will be very thin layer of skin of nanofiber will be formed, and that will be a basically completely biodegradable skin, which will prevent and help the burn patient to recover fast. So this is we have already done, and this will be in the market maybe this year itself, because we have to do some clearance as well as some modification in the drug. Again, the air filter, of course, we are standing in a place where it is water is not a problem, everything is a problem. So where what to do? So we have created something, the filter, not entirely the air filter, but the air cartridge, which can be fitted retrofit with any of the air filter which is available in your home. So this air filter has a very simple and unique technique which fits with the existing air filtration, but you can easily see the change in difference between the existing filter and using our filter by naked eyes. The existing filters, they are only coming up with HEPA or ULFA technique, that is I explained earlier. But this, if you attach this NHEPA filter, you will actually see the finest particle which are really harmful for your lungs and your body. That is basically filtered out with the using nanofiber filters. This is again ESA filter that we have created. This is the industrial DuFuGuard, industrial air purification technology, where the manufacturing nowadays, India is growing towards the highly skill and technical manufacturing. But again, we are not addressing the issue that is related to health and manufacturing processes, including cutting, milling, or maybe welding, anything. If you visit any of the company, nobody wears nothing. Okay, they are just doing like whatever they want to do. So how one can address that? So this is a technique where it will be attached to the point where you are doing the work. It will suck the air, filter out the air, and again it will reproduce that air. Again, it will clean the air into the room, and again that air will be passed in the room. Okay, I'll just leave this thing okay. So future opportunities and startup, that is related to you can see these are the numbers are related to something where we really have to look, and that is how the business works, that is how the startup works. So one side is the technology, one side you have to do the market and the business analysis. Business analysis is something, if I start today, where I should be able to reach. You can see 2023 to 2030, the nanofiber market is going to increase uh, from one from uh, 1300 $1,382 billion to $6,940 billion. Million dollar. But which are the sector one should target? So as I said, these are the areas where power, healthcare, textile, water and air treatment, chemical and others. But mostly if you focus only on the healthcare and water air filtration technology, even you can able to reach to the large level. What are the technique? I already explained, and there are many things can be done. And so see, so many ideas, so many problems, so many solutions. We really have to work on the one problem, one solution. So if you target and address 5 elements of the earth, we are already working on the 2 elements of the earth. But many times, many things, many people, many students, they used to come to me and asking what to do. So the question is always like, many times we have been taught, try to think out of the box. But I always used to say there is no box. Okay, you just have to think infinitely. And more than that, we really have to think completely differently. And how it can be? So it's a very simple example. And the example is something: think big, think different, be confident. And why so important is that the problems are very simple and the solution is more simple than the problems. Okay. And we are working in the environment. India is something where we have a lot of problems. If there are a lot of problems, that means there are many solutions. So how one can address these problems and the solution? So think big, think different, and be confident. So it's a very simple example. We pay to kill cockroaches, right? We buy the heat, we pay kill cockroaches. But in Thailand, they pay to eat cockroaches, right? So it's very simple. Like in Thailand, they pay to eat cockroaches and spiders. So what will be the solution from the Indian side? Market is there in Thailand. The Indian side has to catch the cockroaches, make the pickle, and sell them to Thailand. That's simple as like, So why I'm here? Because being an academician and researcher, I thought let's translate technology from the lab to the commercial level. And that is where this is the picture you can see between academia and the industry. There is a huge gap. One, the patent is published, everybody forgets the patent because patent is published by the student, okay, and also by the professor. The moment you go for the commercialization, there are a lot of challenges, lot of problems. It can be addressed by both student and academician and the professor. But the time comes, only professor is there, student is not there. So we'll address the problem. Okay, don't mind, sir. Okay, many people are sitting over here, but don't mind it. This is what happens because this is I have gone through already. So we have to be very serious about this problem, that how the commercialization can be taken place in the Indian scenario. And these are the opposition and opposition and the parties. They're wearing our mask always in the during the COVID and nowadays also. You can see all celebrities, even Congress and BJP, they're wearing our mask. And there was a time where our Prime Minister was wearing this mask during the Ayodhya Puja. And thank you so much. If you have any questions, I will not be happy to answer them. Yeah, please.
I can take that privilege for use. So, Sandeep, very nice talk.
Thank you.
Because you concluded on that picture that, and you raised the concern that there's a gap between industry and academia, and this is a debate. I would say that these days, and it's a hot topic between industry and academia, of course. So, what are your thoughts on it? Because see, I sometimes feel that that overall, I'm talking not. There are some examples, some specific examples, but they are very few. That overall industry is not ready, perhaps, for the research. The kind of the see, academia has its own expertise, and industry has its own expectations, right? So, how to bridge that gap? Because whenever we think about industry, so first thing comes into our mind is essentially the projects that have to be delivered on time. So that is essentially a sort of consultancy. But what is so what I understand, in addition to that, there should be some research projects for longer time that may also help in bridging the gap, the so-called the gap between industry and academia. What are your thoughts on it, Sandeep?
See, yeah, is we started from the same place.
Yeah.
I took a different route and you took the different route.
Correct.
One thing that is in common with us, that is a research. Second one is the research and academics. When I started and working closely with the professors and industries also, the thing is like industry has a completely different perspective, and that is basically business and money should go together. See, bigger industries, even though they don't spend money in research, they know research takes its own time, commercialize and come up with a product. They always want the time limited research, and there where we fail. So if there is a time, like let's say they are considering that it should be done in 6 months or 1 year. So academician at least should be deliver 80% to them. That is what I feel. That is where we fail. Why it is? Because the product cannot stay like in the papers. It should come out from the paper to the level where it should be commercialized. Now, how to address this? The address is this. And the solution is this, like we should involve academicians, industries, not only as the project sponsor. Like, I given this proposal to even to IITK that even your MTech thesis, PhD thesis, one examiner should come from the industry. Why? He can just sit, see what is going on. That is one. Second, if they are sponsoring any of the projects, see, in India, academics, only 10 to 20% of the industry sponsor project we could able to attract. The rest of the funding comes from the government institutions. Why? There are the things are time deliverable milestone that we fail to do. Even I am working with Australian government and Australian universities for the projects. So the difference that I feel there and here, like, if I want that this should be done, at least 90% work is done by them, right? But in India, that is little, what you call little not taking seriously, where we have to come up with that seriousness to the deliverables. More than that, I said one is the academia and industry. Industry should be invited largely on the platform where research is displayed without money. See, so most of the time our interaction is always money involves, but we should have this kind of stuff, like, only not the academicians are in the thesis and this thing, but the industry can also be involved. I mean, like, that is what my views is. I don't know. I mean, like,
Thank you. You gave one thing essentially for
Yeah.
me to essentially think about it.
Yeah.
Yeah. Thanks. We'll
Yeah.
discuss more on that.
yeah, sure. Thank you. Yeah. Okay, so I think it is done. बसंत जी, मेरा टॉक खत्म हो गया.
I know. I visit sometimes your place.
Okay, so I'll wind up my stuff. Yeah, thank you so much.
But I know that you are a great speaker.
We extend our heartfelt thanks to our keynote speaker, Dr. Sandip Patil, for delivering such an inspiring and thought provoking presentation. Your insights and expertise have greatly enriched our understanding. We would also like to express our sincere gratitude to our session chair, Dr. Suvandan Saraswat, for his exceptional efforts in conducting today's session. Your contributions have been invaluable to the success of this event. Now, I would request Dr. Basant Sikarwar and Dr. Suvandan Saraswat to felicitate Dr. Sandip Patil. Please give a big round of applause. I would also request them to felicitate our session chair, Dr. Suvandan Saraswat. I would also request them to present a memento to our distinguished guest, Dr. Rajesh Prabhu. Thank you everyone for having this session. Now you can move towards E2 auditorium for technical poster presentation.